Thank you for the introduction. This paper is a result of collaboration between the University of Northampton and Shanghai Ever Power Technologies Limited. I would like to acknowledge contributions from my colleagues from Shanghai, Dr. Błaszczyk and Dr. Lei, and Dr. Smith, who is a visiting professor at the University of Northampton. The outline of the paper is as follows: a brief introduction, considerations of energy consumption, power requirements, power supply and seasonal energy fluctuations, discussion of PV solar panel outputs, power supply systems and energy storage strategy scenarios, calculations, results and cost estimates, and eventually conclusions. In the introduction, we'll consider the traditional drive system, which must be capable of four-quadrant operation. Power from the mains is supplied in the first quadrant when the system is raising the out of balance in the car, and in the third quadrant when the system is raising out of balance in the counterweight. Part of the supplied energy is then stored as potential energy. On the other hand, in the second quadrant, lowering the out of balance in the car, and in the fourth quadrant, lowering the out of balance in the counterweight, the potential energy is being given up and returned to the mains. These scenarios are shown here in the flowchart diagram at the left and the right accordingly. This diagram shows the basic components of a variable frequency drive system connected to the mains. In the example shown, this system includes a control microprocessor and a synchronous motor. We can then be confident that the motor speed is determined exactly by the equation shown above, and given in terms of the frequency of the supply and the number of pole pairs in the motor. The motor then follows the speed pattern required. Having established the background information about the drive systems involved, now we'll move to a simplified model of the lift installation. This model has been considered to generate the lift system energy usage requirements data. The building data and the lift installation parameters are shown in the table. The lift simulation model was implemented then in the commercial software package Elevate. And the model involves a 30-floor building of height about 112 meters with the lift installation of conventional arrangement for a single deck system. The simulation is based on Sequent full-day office 24-hour passenger demand template, also shown on this slide. A sample set of simulation results are demonstrated on this slide. You have two diagrams here. The first diagram illustrates the simulated cumulative energy consumption of the lift, and the second diagram shows the lift energy requirement over time, derived from the first diagram. Taking into account those data, it can be established that the total daily lift energy requirement for this model is about 117 kilowatt-hour. We'll now move to power supply and seasonal energy fluctuations. We'll assume that all energy needed to power the lift is to originate from solar panels. The seasonal energy imbalance fluctuation will be considered at the following two locations: at the equator and at the 52-degree north latitude, which is about where London is. And those to be covered in the following two scenarios. The first one, when the mains grid access is available, and the second, the mains grid access is not available or not possible for some technical reasons. Now we'll discuss PV panel outputs and we'll compare the outputs with daily lift power needs. This diagram shows the outputs of PV panels against the daily lift power needs at the equator. It illustrates the maximum, in blue line, and the minimum, in red line, outputs in watt per meter squared of PV panel area, together with the lift power requirements in green, also expressed in watt per meter squared of the panel area. The lift power requirements don't quite correspond to the available sun energy periods during the day and night. Therefore, we'll propose a buffering battery bank to be charged from the solar panels to compensate and cover the energy needs. In that case, we'll not apply grid power supply. Based on the data which I illustrated in the diagram above, the required battery size was determined as 79 kilowatt-hour. The required solar panel area is then determined and given as 51 meter squared. And this is based on the minimum energy, the area which is below the red line. This diagram shows the outputs of PV panels against the daily lift power needs at the 52-degree latitude north location. It is evident that the lift power requirement curve, again in green, is now above the minimum solar PV panel output curve, again in red. Thus, the situation is dramatically different. The corresponding power supply strategies to cover the daily lift requirements will be discussed next. Let's now consider a bigger picture. We look at the power supply system and the energy flow block diagram shown on this slide. This involves a variable frequency drive with the rectifier part removed, and we'll discuss 2 locations and 4 strategies. At the equator location, solar panels charge a battery bank, which covers the daily energy requirements. The yellow path applies, and what is involved are the solar panel, converter 1, buffer battery bank, two-way converter 4, and the drive. At the 52-degree north location, in scenario 1, the grid energy is stored in a battery bank. The mains, converter 5, components in blue dashed line are added. At the same location in scenario 2, for the PV panel use alone, and to apply the yellow path, a large battery bank required is too expensive. Therefore, an alternative solution is sought. The green path is added, and this represents fuel cell solution. The excess sun energy during high radiation periods is converted into hydrogen through water electrolysis. Hydrogen is stored in pressurized tanks and then converted back to electricity in the fuel cell at the low irradiation periods. So the green system consists of converter 2, electrolyzer unit, hydrogen storage tank, fuel cell power plant, and converter 3, which feeds energy to buffer battery bank. Summary results and comparison, of course, is as follows. At the equator location, solar panels charge a battery bank covering the daily energy requirements. The battery size is 79 kilowatt-hour, PV panel surface about 51 meters squared, and the cost is about $25,000. At 52-degree latitude north scenario, for the one option, when grid storage is available, the grid energy is stored in the battery bank. We'll use similar battery to the equator location, however larger panels of total area about 63 meters squared. The cost is slightly higher, about $27,000 to $28,000. The scenario 2, when there are no grid storage available, we need to use very large battery in order to satisfy the requirements. This is not feasible because then the battery size is prohibitive, about 11,000 kilowatt hour. The costs over 2 million. Therefore, we considered fuel cell solution, and as an alternative, it is much cheaper. That means we are using similar buffer battery to the location at the equator. The PV panel is slightly bigger, about 80 meters squared. Adding these costs, we arrive about $300,000. It is substantial, but much cheaper than the previous option. Let's draw some conclusions now. These are as follows. There is no need for seasonal energy storage in the areas close to the equator due to the high solar power availability for the entire year. But seasonal energy storage requirements arise at the locations away from the equator. The simplest and most cost-effective way to deal with the seasonal energy storage in these locations is storage of energy from the grid. In the scenarios when no grid access is available, we consider two options: the seasonal battery bank and the hydrogen storage in pressurized tanks to be converted back to electricity in the fuel cell. The more cost-effective solution is storage in hydrogen rather than in battery. However, it should be mentioned that the use of hydrogen storage tanks might result in safety concerns. The main hazards are related to the properties of hydrogen, fire and explosion, and there are also some electrical hazards. So overall conclusion is that the development of a grid-independent lift energy supply system is feasible. However, the cost, space requirements, and risks involved need to be considered. Thank you very much for your attention.